still is so maybe we should have done it up there, but I'll be talking a little bit about what I've been working on the last year or so of my life, trying to obey the whims of the powers that be and doing AI for physics, because that's the future, right?
Present.
The present.
In the present, yeah.
You don't have to be afraid of your findings.
I'm sorry?
You don't have to be afraid of your findings.
Well, maybe there's a reason why I have so many. So I want to take a second to remind myself that I'm not just an AI person, I also do physics. So I like this picture of sort of a bunch of resonances that have been experimentally observed, at least find evidence for at the LHC specifically, because there's this guy that produces nice plots like this. I like this plot because it sort of shows the sheer volume of data output from big machines like the LHC, and sort of like the amount of resonances that require categorization and study and analysis in order to be able to say more about QCD, about being able to actually solve it from first principles analytically. So this is sort of just like, there's a lot of stuff to do, a lot of data to analyze, and people like me get to have fun and analyze it. There's a whole zoo of resonances with various possible explanations for, important content or exotic descriptions of those resonances. There's many tetraquarks and pentaquark candidates on the screen before you. That's not to say that we know everything there is to know about even the simplest resonances, like ones in pi scattering. So I want to sort of motivate that by showing you the state of the art of description of pion-pion scattering at low energies. So on the right hand side is a plot of the scattering phase shift of the isospin 0 S wave in pi scattering below about 1.4 keV from sort of the paper to end all papers in terms of analytic descriptions of the amplitude. This is actually a plot I grabbed from paper number 4 in a series of papers, which span a crazy amount of work, truly real effort to parameterize pion scattering. And I want to note that it's really important that information about pion scattering is well understood, because this stuff appears basically in all reconstructions of resonances and all particle in all detectors. There's pions flying everywhere. It's just important to know what's actually going on when you're scattering these things off each other. I want to note that the data comes from a lot of old experiments. So plotted here is a selection of some experiments along with their fit to the data. And many of those experiments are indirect analyses, and there's problems with them, and we'll describe those in a moment later in the talk. But I want to take a moment to point out that there's actually error bars plotted, or there's a Gaussian error band plotted on this picture directly from the Bible of pi scattering. And it's very small. It's hard to even see it at some points, depending on which energy region you're looking at. Okay, I have the cursor, but even down to the lower energies where you'd expect like a signal to appear, you can't even see it, which indicates sort of like room to do some more work in the realm of error propagation, the realm of big data analysis to get a better line shape that works for fits. So the data is old, data sets are actually compatible. We can see some data has really small errors and but other data points. Errors really are underestimated and even best fits that people come up with over the years.
Why are there no new data for finding?
If someone would please build me an experiment, I would love to have new data for it. I think the reason is just that it's old and not very exciting. There's no exotics really that are going to appear up in the energy region. It's pion scattering, so there's something you could do. So why would you do that when you could build a $30 billion machine to find something random? I don't know. It's not very exciting, I guess. It's hard to use the pion beam. Yeah.
And some of the error here is really hard to narrow down. So you always have the off shelf that's. You don't have a full pion, right?
Yeah, it's hard, yeah.
So I think what often do they do?
How do they get the experiment?
They get a pion beam and they pulse the growth film. Yeah, they take a pion beam, they hit it off a fixed target, I think. Knock out another pion and then look for the 2 pion correlation coming out and tease out on something.
Yeah.
So extrapolated to the pion pole exchange, and that's where like all of the ECP, for example, that like that.
Yeah, I mean, it also suffers from I mentioned this later, there's operational problem with ambiguities in that you can't even directly resolve partial content of the intensities that are coming out of whatever indirect discriminant you have because of zeros in the ambiguity. You can have like complex conjugates of zeros in the. Yeah, so these different solutions indicate that there's multiple reasonable guesses or models that will describe and produce the partial ways for those two. So
But-
there's.
I guess what I want to say is like, why do these challenges motivate people to do more? I mean, I feel the same when I'm talking about the Python PDFs from the phenomenology. There are always this super old data sets from the 80s and 90s that everyone is relying on. And I'm wondering why was this not the motivation to do more of it? What happened in the 90s? Everyone was like, okay, let's drop this.
It's fine that he's also super symmetry.
Yeah, I don't know. You.
Well, there's also that one data set that was weird. Oh, sorry.
Oh, so you data set from Russians or the young students.
Yeah.
It's E plus E minus, yeah, but still a good behind.
So at least it's delta one, like isovector.
The isolated form factor, yes, that's right.
Yeah.
But
Oh,
that's
I
not
mean,
the F0.
But this is the isoscalar.
Yeah, yeah, so I guess it hasn't made its way into my hands, or at least this paper is a few years old at this point, so obviously we wouldn't have had access to the connection. But data selection is a problem, and we'll describe that in detail. The good news is that the solution to everything is AI. So, this is my slide. So, I always think it's interesting. Yes, it will back to the ends. I think it's interesting that people always say, "Oh, you should do AI," and no one ever says like what kind of AI you should do, or like it's really hard to figure out what are the pros and cons of various approaches. So here's four ones that you may have heard of. The one that I'll be talking about mainly today are neural networks. I've compiled like a very short list of some good things and bad things for reasons you don't want to use each of them. Neural networks are fantastic as interpolators. They're extremely flexible and they're easy to sort of build in physics constraints into training. And luckily for us, are also fast to train. The major downsides of using them are that you can only do interpolation. You should not ever try to evaluate a neural network outside of the region where you have data. So we'll have to describe ways in which we're getting around that, the ways in making sure we're always interpolating the moment. And also, if you're doing a single neural network fit, you can't really propagate error for that fit. That's just an open problem in computation. That's really difficult to use that shit. So you need to figure out a way to do error propagation. Gaussian processes produce good uncertainties. They're not parametric things, similar to neural networks, and they're very smooth. The reason why they're not exactly ideal for our use case here for kind of scattering data is that they can be a little bit slow to train, and they are quite sensitive to noise, and they scale poorly with increased data. We would like to use as much data as possible, and we have really noisy or bad data, so this is not ideal.
Noise means large error bars, or what do you mean by noise?
Conflicting signals, really. By noise in the data here, I'm referring to different experiments that have widely different values outside of their own error bars. So I would interpret that as noise away from some true value. Yeah. Variational autoencoders are another option where you're basically making you're mapping into some abstract feature space, which means that you could, in principle, try and rig it up to directly encode information about poles and amplitudes directly, get the analytic structure right in your AI machine learning model. But really, it's killed off by our data quality here, and the features can be somewhat hard to interpret. So just because it's possible to encode analytic structure doesn't mean that you should or that you'll do it in a reasonable amount of time. And then my favorite one is the large language models. The pro is that you will always get an answer. They are designed to respond to you immediately. The con is that they almost always lie to you when you ask them about physics. So, on the right, I have like a short little picture of what some of those various options might look like. ChatGPT usually is good for confirmation bias, not just. So we'll be focusing mainly on neural networks. And the overall strategy is going to look something like this. I don't know how to solve QCD. I don't know how to actually write down and build an equation that describes all of the physics, how the dynamics involved, and even pion-pion scattering. So what I'll do is I'll build a neural network that takes in energies and tries to spit out all of the scattering phase shifts and elasticity for all of the data that I put into it. Just to know, the phase elasticities are directly related to the partial waves and some usual partial wave extensions on top right. Doesn't really matter what formula they are, we're taking the data for the phase shifts and elasticities inputs. In order to do actual error propagation, we're going to steal some of the NMTDS homework. We're going to do a resampling on all the data. So we'll take even our faulty data, resample within the error bars, and to retrain copies of neural networks on those resampled data in order to produce like an ensemble of statistical output, basically, that preserves statistical properties of the resampled data as we put it in. So this is how we'll get our error bars, and we'll get some sort of Gaussian line shape around our interpolating this. All of physics here needs to use force through some additional manipulation of the loss function or through what I'm going to call hybridization of the neural networks. So we'll have to put on guardrails to make sure that we satisfy things that we would like to satisfy. And really the idea is we want to validate this type of process for the simplest possible situation, time scattering below 1 GeV, and see if we can get stuff like the row with the sigma out of the entire procedure. Good so far.
So your network knows about all these equations up there, or you just
No.
blatantly train this and hope for the best? But I don't know.
Yeah, so the network doesn't, I'm not putting in the equations from the top right. The data that I have is already in the form of the elasticities and the phase shifts. The top right is just the connection for the partial wave amplitudes. Just a partial wave projection.
So you don't do a data analysis of partial wave analysis of the data. You rely on their extraction from the data.
Yeah, or I guess they are, yeah, so technically the data that I have is from parameterizations of the partial waves written in terms of the equations from the top right, yeah. So I definitely could have started with the ones from the top right too, and that would have been valid as well. Just a different type of, just the data that I have is in this form, so I guess. So not that it couldn't have worked either, yeah. A note about neural networks just in general, what they are, they look something like this. The way to think about them for interpolation is you should just think about them as just a really complicated function, some sequence of linear transformations and nonlinear functions which produce you enough wiggle room that spans a large enough Hilbert space that you can describe whatever it is you want to describe. So this picture right here is a neural network with two different layers. These two different layers are these two gray layers in the middle here. Here I have an input layer of 4, which means this neural network takes in like a 4-dimensional input, for example, and then this one gives me 2 observables as output. For our use case, we're basically putting in energy and getting out the entire set of phase shifts and elasticities. So we'll have one single like circle on far left and then sort of a wider version far right. And sort of no matter what structure of neural network you write down, you can always decompose it into a sequence of linear transformations sigma, followed by some nonlinear functions f. So this complicated neural network basically means take your input, take your vector of x's, multiply by a parameter matrix sigma 1, for example, 1 being the first layer, hit it with a nonlinear function f, then proceed to the next layer. So the next layer you hit it with another linear transformation here, sigma 2 corresponding to there'll be some 4x3 matrix of parameters, hit it with another nonlinear activation function f, and then do another set of transformations to get the output. So really, functional decomposition looks exactly as it is in the right. That is the explicit form of this neural network without writing down all the parameters and code. So you can make these things as big or as small as you want in terms of number of layers of neurons. Neurons being each little node here, which has connections between the previous and next layer. Or in terms of the activation functions, you can change those basically at will, so that you can produce a universal equivalent. While you can write it down, you really don't want to, because frequently it'll take up several blackboards worth of space. So even though it isn't really a black box, it might as well. Yeah.
Okay, so talk about another thing, but input and energy, you get out a bunch of ratios. Okay.
Yeah.
But it's good.
I thought you input energy and phase shifts from all experiments.
So you put in the energy and the neural network produces you a prediction based off that energy, and then you adjust all of your weights to make sure that your output matches the data. So it's sort of like calculation of the chi-square, and we'll get to that in a moment.
Okay, that's
So,
what I was after.
Yeah,
Okay,
so The neural network itself is just a machine which has the functional form that
Which
you
makes a
want.
multi-dimensional.
Yeah, it makes a multi-dimensional thing that you want, and then you should train it on a loss function that respects physics and information. So,
I have a quick question, what are the signals?
the sigmas on here are just linear matrices, they're linear transformations. So it's like, going from the x vector to the first hidden layer. It's multiplication by a 4x3 matrix to produce, a column vector with the right output, with a three-dimensional output. So here, there's basically a vector of dimension 4, here's a vector of dimension 3, here's a vector of dimension 4, and they're just propagated forward between their transformations that map from 4 to 3, basically, so on.
Did you say the signals contain parameters?
Yeah, those are all parameters that are floating, and then they get adjusted during training.
But they're not like physics parameters. They're
No,
network parameters.
Yeah, they're network parameters.
Yeah, okay.
Yeah.
I just like the width of the hidden layer.
How do I select one?
Yeah, anyway.
Well, okay, this is more complicated than I can describe in a sentence. Guess and check, honestly, there are some notions about like the width of the neural networks, the number of neurons in a layer corresponding to how many features you might be passing forward. So you think about like expansion being like, look at the smallest possible bit of information to think of in your data, and compression being like synthesize or combine features to make sets of parameters that consume more large scale information, but it really is whatever works for your case. You can do hyperparameter optimization, which includes selecting the number of neurons in each layer, number of layers, types of activation function on all of this. But that would only be really important if you're finding that it takes too long to train, or if your results aren't very good. If you have a network that works, then it's interpolating the right functions, so it works. Yeah.
Since we're on this slide and keep getting asked questions, I'll throw it in too, why not? Is a sigma matrix, in this particular case, 4x3, essentially gonna be 12 parameters to get optimized?
Yeah, okay, exactly. Yeah, all of them are gonna be real, like usually floats or doubles. They do not allow complex parameters, fortunately. Typically, it's not efficient. So we have a neural network structure, and then actually we're doing, let's call this a split head shared trunk hybrid neural network structure, meaning it's this picture on the top. So I'm sending in an energy or square root of s. I am basically saying, okay, like build me some neural network, some shared trunk neural network, which sort of contains information about all sorts of correlations between the various data, and then splits it out into various information corresponding to each of the data that I have access to. So then each head is another smaller neural network, which specializes to train each of the observables that I have access to, making sure that I am able to fit individual line shapes for several different partial widths without having to extremely increase the number of parameters in the shared trunk. So this is what basically compresses the amount of parameters my neural network to. From initial attempts, I had neural networks that on order of like 50,000, 100,000 parameters, and the ones I'm currently working on that are working fantastic have like 1,500 parameters. So this structure minimizes the amount of stuff I need to parameterize by splitting out correlations from the specialized software channel. So I think I said that bullet point. What's important to note is that traditional methods for fitting all these observables do not maintain correlation between waves. So even just writing down the structure, I've already done something sort of like new and interesting. I've guaranteed that all of my fits for single partial waves, about all the other partial waves, or even setting, which is nice. Yeah.
This is like, are you feeding just like a single energy?
Yeah.
Do you lost correlations across entities?
Oh, I feed during one training run, I give it all the data that I have, so I'm feeding all edges.
Okay. So when you mean root S, you mean like all possible root S?
Yeah, I mean, it's vectorized over the entire set of data. Yeah. So for an individual evaluation, I am producing, for one energy, I'm producing all the outputs, and then when training, I'm feeding in all data I have, so all energies and to all outputs. So yes.
So you say you have 1,500 whatever parameters, how many data points do you have?
About 1,500. We'll get to that in a moment. Yeah, so after I produce some neural network output, then I push it through what I'm calling a post-processing step, in which I'm enforcing some specific information about that partial identities that I require for the outputs to be real and physical. Here, the post-processing is basically what makes this a hybrid neural network structure, because the output isn't just neural network and sticking on some known functional quality. And here, I'm enforcing the fact that physical inelasticity should not be above 1 and less than 0. So this 0 is less than equals less than 1 is a hard requirement. And I'm also putting in information about the behavior of the phase shifts and elasticities near thresholds as they open up. There are several thresholds in my energy region, and I need to make sure that I'm producing the right behavior of the partial load as I approach those thresholds. So here, actually, like mass of the planet, for example, and masses of the thresholds that pop in are stuck in the post-processing layer as sort of hyperparameter that I should know about. So basically, I've taken mass of the planet as a hyperparameter, I've grabbed from each of the references. So this is my structure, and then the physics that I want to enforce, that I will have to enforce in loss function are these S-matrix principles. At this point, it feels like illegal for me to not have a slide like this in all of my talks, because I talk about it so much. The idea is that whatever our output is, we want to make sure that we preserve the analytic structure of magnitudes. We want to make sure that we have causality or analyticity in the physics output in the neural network intervals. We want to make sure that we are respecting unitarity, and we want to make sure that we have cross-symmetry built into our model. So if we satisfy these three things numerically, then we say, okay, whatever we get neural network is valid, it has valid for use cases elsewhere in physics for propagation building issues. So the way we do this is primarily through careful selection, careful building of the loss function. So the loss function is a function that we minimize when training a neural network, when basically going through a back propagation algorithm, addressing all the parameters. We are fitting the data, so we have a chi-squared fit in the loss function as a matter of course. When you have good data, it's really easy to minimize chi-squares because neural networks are so flexible. Actually, more often we try to adjust the neural network to make sure they're not overfitting the chi-squared and then like 0.0004 whatever chi-squared you have. Also, because our data is physically meaningful, the data is unitary, and the stuff we have access to, the base shifts and consistencies, is sort of a unitary conversation itself. So we would expect that if the data is reasonable, then this helps us get closer to unitarity for the output if we're describing the data properly. So the second term, lambda rho delta rho, is a term which captures the satisfaction of these so-called rho-like equations, which are basically this version relation for partials that we have access to, which I'll talk more about in the next slide. And then the next term, this lambda SL delta SL, is an extra penalty for making sure that we're getting the threshold behavior right, the elastic threshold behavior right of the various partial waves. It sort of really makes sure that we're not doing anything crazy right at the pi threshold. So really the meat of the matter.
What is the main to getting consistent scatter?
Yes. So maybe I'll just answer your question first. So the word equations are the thing on the top. The subtraction terms, these STLs, correspond. Well, so this is a subtractive dispersion relation, meaning that there's some parameterization put in order to minimize the effect of high energy and no nonsense in the relation.
Wait, the right equation is if that were 0.
Yes.
Yeah,
Yeah, so it's phrased as a minimization problem. We want this to be as close to 0 as possible. Yeah. So the right equations are satisfied. The one that on the top is 0. And subtractions have the scattering lengths of the S0 and S2 scattering lengths built into them. So the only place in which we have the scattering lengths currently, like without the subtraction term in the model, is through the Roy equations. Now we're minimizing the Roy equations. We're not necessarily making sure that the actual amplitudes have that scattering length that's parameterized in the Roy equations at the actual value of threshold. So the subtraction term, the thing on the bottom right, is basically saying take the parameterized scattering length from the Roy equation and make sure that it matches what we're actually calculating at the pi threshold. So we're double penalizing non-visible behavior at thresholds. whatever value we have in these subtractions must match whatever value we're actually calculating with the null network.
For the non-initiated about that, so this little TLI at the very end, they take the imaginary part.
Yeah.
What is this? This is some kind of a T matrix or?
No, that's the partial wave itself.
It's a partial projected T matrix. Or
Yeah.
I
Yeah,
suspect-
but so when all you put in are phase shifts, right? I mean, and energy.
Yeah, so I'm running it through those equations that were in the top right.
Okay, so, okay, those you put in.
Yeah.
And then you do the integrals on your energy, whatever prediction energy curve.
Yes.
And then, okay, got it. All right.
Yeah,
And this
so,
KL is some kind of fancy schmancy kernel.
yeah, they're, exactly, they're
Okay.
some fancy kernels that are, yeah. Horribly complicated, and there's a mixing of the various partial spins. There's all sorts of nasty things going into the integral itself, yeah. Did I answer your question, Noel?
Yeah, we're talking about that or like it seems.
Okay, let me say it really simply. The A zeros appear in the scattering, sorry, in the subtraction terms. But that A zero in the term is just a parameter until we connect it to the actual value at threshold. So we're penalizing any deviations from the value at threshold.
Yeah, I mean, you're saying, like, you can satisfy the Roy equations. And the subtraction parameters that appear there. You don't have to just turn down the middle threshold.
Correct. Unless we double count, basically, unless we do those. So this it wasn't, I put this in by hand because I noticed that I was getting good fits and then I looked at threshold and I was like, that can't be right hand. Because it's basically like way off from one another. Because the Roy equations also give a elicitation of the event itself, and it relates to the real imaginary parts of the too. So you can rewrite this as just rewriting the amplitude in terms of the imaginary part, doing some fancy stuff. More on that later. And I noticed that they were diverging. Neural network output and the Roy equation version were different because it wasn't doing this.
Is also wrong in something, those constraint as well?
Yeah, so they did Roy equations. They also did,
Yeah.
oh no, because theirs were built into the models. Yeah.
So these are other people who have done neural network.
Yeah, no, not neural networks. The first,
Just
these
a
guys.
regular ice
Yeah,
cream.
the pion experts. Yeah, big Spanish group. Where was I? So yeah, those are the Roy equations. Honestly, the less said about them, the better. They just enforce analyticity and crossing because these subtractions and crossings will fit. There's some high energy Birge stuff in the DCs. Basically, after a certain maximum S value, we don't really have good information, or we don't have data, so we can't really evaluate mathematics about that. And so we're at some point cutting off the integral and parameterizing the rest as a high energy Birge, which also is standard according to Husserl and others. So yeah, so this is really doing the bulk of the physics knowledge, putting it into that application. In order to do this properly, you can't just put it in and then write your first neural network and pray. You kind of have to do it in a way that makes sense in a smart way. And so because single fits aren't enough, you need to repeat thousands and thousands of bits, thousands of training runs. So you really need stable learning methods to do this over and over again, even on recent pages, noise like that. The two or three biggest things that were important in order to make all this work is what's called curriculum-based learning. So the curriculum-based learning methodology is sort of depicted in the right. The idea is that at the top, you basically have some graph of like your error versus your time. Time being computer time, being how many times you feed all of your data through the neural network to make sure that you're training on it. So the longer you train, the more times the neural networks experience the data and try to fit those data you have access to. And the idea is that as you move forward in computer time, you switch to harder and harder problems. So you have some curriculum scheduler which says, okay, I'm pretty early on in the training process. I will try to learn an easier version of the loss function. And then after I've learned enough of the easy version, I will then move on to the medium or harder versions. What that looks like for us here corresponds roughly to this curriculum in the middle of the screen. where I'm adjusting the various coefficients of the parts of the loss function, basically turning them on or ramping them up in order to start from a simpler, less constrained problem and gradually impose more and more constraints and produce something that actually fits the data and satisfies all of my physics stuff. So I'm always putting in the data that never changes. The Roy equations and the scattering elasticity are sort of we start with nothing, we start with new knowledge of them, and then there's this extra parameter omega chi, which actually turns on or off, reducing the strength of the various weights of all the data. So all of those error bars that were everywhere, if you just throw in the full chi-square right from the beginning, you will get completely another gibberish because some of the data has extremely tiny errors and some of them have extremely wide errors. Starting from an uninitialized neural network, it'll produce some totally random output, so you'll get thrown off and totally random direction from the start. So I'm gradually basically increasing the strength of the weights to when the amount of these errors are propagating into the neural network and producing the next way forward, and similarly increasing the weight of the Roy and scattering length consistency checks. Note that the scattering length consistency check really should be infinite because the value must match that threshold. I'm stopping at 10 because it seems reasonable enough, even though I know that 10 is far away from the so in doing so, I'm producing about 300 parameters per neural network. And another extremely important development which has made this possible is Jacobian descent, which is different from gradient descent, meaning that the algorithm that I'm using to minimize the loss function with all the neural network parameters sort of is taking the entire vector of losses for each partial for each data that I have and minimizing them all simultaneously, as opposed to just adding them all up and going in some generic gradients. So you're going in the direction of decreasing Jacobian as opposed to the direction of decreasing gradient. Quite nice, very, very good development. Highly recommend this if you are doing comfortable fix. So
why is the constraint on the scattering length the one that is the most imposed from all of them?
Because as I mentioned in practice, or this value really should be infinite. Because there should not be any difference between the parameter in the Wyatt equations and the actual value of the equidistant thresholds. So I'm stopping at 10, which seems to work fine because the losses, that part of the loss gets very, very small, as I'll show. And probably the next slide, actually, 2 slides. So,
Like, for example, the Roy constraints are truncated in some sense, so you don't have to impose them as heavily.
yeah, so I could increase these basically as I would want to. The actual values in this table are based off of the experience of doing hundreds of thousands of bits and then figuring out like appropriate values for them. Not necessarily that these are correct absolute final values of what you use. In principle, I would hope that all of these are infinitely strong constraints, I guess.
But the Roy equations are approximate. They're all I mean, they assume like all your exchanges are associated with 2-particle system, 2-particle exchanges.
Yeah, and even worse than that, because I'm doing a truncation and discretization, they're even more proximal.
Okay. Meanwhile, the scattering with the threshold is defined by scattering.
But I thought getting the scattering length right is arbitrarily complicated because nobody measures them. And you always have to repeat practice. So maybe I'm missing something with your scattering length. I'm surprised that with such a hot constraint on the scattering length, it's very hard to determine.
It helps overall health of the fit.
It can be precisely wrong or approximately right.
Yeah, well, I'm not saying this is the scattering length. I'm saying the parameter that I produce must match what I'm claiming is the value of threshold. So I'm not putting in outside information. Maybe that was
right, so that's exactly what I'm missing.
So I could put in actual values and that would be not correct.
Okay.
There are 3 parameters. The consistency is itself consistency. The parameter that I fixed here, that I produced from the training procedure, must also match what that same training procedure claims is the value at threshold.
I mean, the Roy equation, the integral doesn't converge an infinity.
Yes,
So,
understood,
they have to subtract,
understood,
and the way they subtract it, the way the subtraction functions are defined by the amplitude.
understood.
The
Yeah,
point.
but now I take three random numbers for these three catch calendars. Or whatever, how many we have, right? And so then what do I do?
So he's fitting the ground,
I'm fitting them. I'm producing a guess for the scattering line.
but the scattering length, so the amplitude, the scattering length are equal to the amplitude of threshold. You just check
That I understand. But I mean, but to enforce it that the scattering length always comes right. How when you know right? I mean that's
Oh, I don't know that.
maybe we talk about the silver lunch tomorrow.
Yeah.
That would be okay, go ahead.
I think there will be a plot that will make sense
Okay.
to that at the moment. This is what like the single fit looks like for a couple. This is just the S wave. On the left is the phase shift, and on the right is the analyticity. Just to show what a single fit looks like before I immediately run the picture by having a bunch of lines everywhere. Yeah.
The points are experimental data,
Yes.
and a single bit is taking, you're doing it, putting in all the experimental data with like error bars.
The error bars are used in calculation of the chi-square.
Okay,
So yes.
okay. It's not the.
Yeah, so it is a weighted bit, it is respecting those, there's just conflicting information from the family. You guys just keep anticipating I'm gonna say, yes. We'll get that, do that in a moment, so there can be nice curves like this is a single fit, on its own, it doesn't really mean that much, it's only when you have an ensemble of fits. But this is what it could look like. This particular fit was done with every single point of data that I had access to, or almost every. I think out one portable experiment because it ruins the fits. But really, the losses look like this as I'm moving from 0 to, in this case, 1600 because I've had some holy stuff in the head. And the point is that every time you see like a jump in the curves, each curve corresponds to either a different part of the loss. So it's not really mean squared error, it's the chi-squared in this case, the Roy and the scattering length, consistency check. And then the total is the black curve, which is sort of basically on top of the data loss. You can see these jumps are basically when I'm really turning up one of the constraints on one of the parts of the loss function. And then eventually at around about 1400 or 1500, I reach a point where in my curriculum, I'm not really making any more progress, so I stop my training, even though in principle I could go up to my predefined cutoff 2000. So you'll notice that the total loss seems to be rapidly decreasing and reaches its minimum at the end of my training, which is nice. The training appears to be effective. And then there's a lot of like fluctuations in the various parts of the Roy, and especially in the scattering line. This is a check as I'm turning up the weights and allowing them to sort of go down in the set towards symmetry. So this is just the type of thing that will pop up that I would look at and use to diagnose if my fits are performing well or not performing well. You'll note that the loss, the y-axis is in a logarithmic scale. So the actual size of the discrepancies for the Roy and the scattering length consistency check are actually quite small, extremely small. 0.1-ish for the Roy equation. So on average, my Roy equations are correct to within 0.1 per data point that I have.
I mean, 10%.
Sorry?
10%.
No.
0.1.
0.1 is a raw value.
In some units.
Yes, in some units, which I'd have to think about for a moment, probably, I don't know, in some units. There is a question of like how low is good enough, how close to 0 must you get. 0.1 is quite good when compared to other traditional fits with actual office.
There's like 1% of your law.
Oh, of my total loss. Oh, yes, yeah, it's so for this particular fit, it's more like, yeah, 1% looks about right.
I guess the blue and the light blue curves are on top of each other.
Yeah, it's mostly,
other two guys are so small.
yeah, it's almost all entirely driven by the consistencies in the data. Okay, essentially. So It's good that we can get the Roy equation so low, basically.
And it's not a worry that the Roy equation jumps up, even though it's very small, the jumping up that you get not a loss, but a gain. This is just fine.
Well, it jumps up because I'm weighing it up by another factor of 10 each day.
Oh.
Right, because in the curriculum.
Okay, got it. Yeah.
Right. So that's me putting my fingers in and saying, do better. Yeah, this has the weights embedded in it. Not the end, all the weights are one.
So when you jumping it up, you're putting a prefactor in front of, for example, the scattering lights. And therefore it's working harder to reduce that prefactor times the loss, times the difference in scattering.
Yes, exactly.
This is counterintuitive to what I remember.
Sorry, say that. Oh, yes, yeah.
Yeah, like for them, the Roy equation was critical, right? Like it put with the large constraint, it's not doing much.
The Roy equations themselves. Well, it's hard to really say that it's doing a lot or little because I'm doing a simultaneous minimization. So I'm not making any attempt to say that the Roy equations are really driving the majority of the features of the resulting fits. Whereas
it seems like it would affect any model. It would look like, oh, I stopped whatever 500 e-bar.
yeah,
All that about oh, there's Roy equation.
no, well, because what's plotted here has the coefficients put in. So, for example, at the very start, in the first epoch, the Roy equations are multiplied by 0.01. So this is multiplied by 0.01. It's not really that small.
So then, sorry, going back to that last slide. So then on the bottom row, when you put the SL factor up to 10, you're saying this is the most important thing here, right? Is that correct?
I'm saying at this point in time, I'm getting diminishing returns than the others.
I don't know why you like the land of 10
Yeah.
compared to 1 to the rest.
Yes.
You're saying this is the thing I want to emphasize, you get right more than anything else.
At that point, yes. Because at that point, there's not really good argument for adjusting the weight of the Roy equation higher than 1.
And that happens at 900, so that's the last green spike, to send that to 10.
Yes. Precisely. Yeah, so this sort of thing is pretty standard in analyzing neural networks and analyzing general machine learning applications. You look at some loss, look at some plots, try and get it to plateau and try and make sure you're getting the physics out of it.
So it's jump in the blue line at 300. Right? Is that coming from that you all of a sudden require the SL and the Roy? And so does that tell you that this stuff is important to answer around the question, right? So that gives you a measure of what that stuff does, and it seems to be doing something rather significant.
You're saying these two.
No,
300. Why does it jump down?
That's exactly when you turn on the SL and the Roy, right? I mean, because before you don't have a signal.
Oh, I see what you're saying. You're saying it's guiding you more towards the direction of the data. Oh, that's an example.
No, I mean, I just make this up as I go, right? But you, right?
Can you go back to
This one?
Yeah. Okay. That's really okay. Yeah. All you just that as well. Okay, but
It's possible. Who's to say? It's hard to say anything with certainty when you're staring at one single fit out of 10,000. So let me move on. I think I'm a little low on time, so we'll try it. We'll just do some brief comments about data quality, and then I'll get to some punchlines and show some ensembles. As I think several people have pointed out, the data is questionable. There's multiple solutions. I mentioned, we discussed earlier, a lot of these measurements, basically all of them are indirect measurements because we don't have like a fixed island experiment as far as I'm aware. This issue of ambiguities pops up in even the best case scenario. The idea is that cross section, or really the partial waves, if you write them in terms of like kinematical zeros, since the intensities always have like the squares of partial waves, there's an ambiguity if you don't have enough information about like observables that you can replace each zero by a complex conjugate. So you can get discrete solutions based off of the degree polynomial that you have. So based off of the amount of partial waves that you have in your system, you can get a certain number of extraneous solutions, which are all equally potentially physically valid, but probably only one of them is real, and you don't have information to tell you which one is correct. And this is probably the reason why there's 5 greater solutions on this plot of the scattering, of the phase shift for the S0 again. I should mention that this is all the blue stuff in between that's kind of hidden by the data is actually an ensemble of several thousand neural networks trained on all of the data in the screen. So despite the horrible mess, I can still produce some sort of neural output. But it's difficult, it's very, very difficult. And the data itself, in some cases, has in excess of a 10-second discrepancy between different data sets. The worst offender, for example, are these points down here, I would say. The Rescue 6 and 13 data sets, which at this point in time, we're summarily removing out of hand because they make it so much more difficult to fit. And then there's also like data with extremely tiny errors down here, and some of the gray switches also tiny errors. So really, a major undertaking was to figure out some methodology of reducing the number of experiments they have to actually look at, figure out which ones are, if not like globally physically correct, at least compatible with each other. I think I'm running very low on time, so I'm not going to go through the whole spiel. I'm just going to show this slide and then we'll quickly go through the next 4 and pretend that they don't exist. The general idea is that, and this idea is also sort of copying a little bit from NPDF's homework. They had some sophisticated ideas about reweighting various experiments in the ensemble of experiments and analyzing the effects of the chi-squareds of other experiments based off those videos. So you start with a baseline set of ensembles, the ensemble that I showed in the previous slide. I've done a bunch of fits. All the data is included in those fits. Fine. Then I do a new set of fits for each experiment, and I upweight that experiment that I'm inspecting, experiment I, so that it is as important as all the other experiments combined. And then I look at the changes in other experiments chi-squared in that ensemble's upweighted, ensembles stuff. So this produces a matrix picture like this thing on the right-hand side, where the rows correspond to the experiment that I've upweighted, and columns correspond to the chi-squareds of each individual experiment for that run. So this is already grouped together in some grouping pattern, but basically what I'm doing is a principal component analysis on this compatibility matrix produced with the formulas in the bottom left. So I'm doing principal component analysis and I'm clustering them based off of some Euclidean distances between the feature vectors, producing stuff like this. So without saying too much about that, I'll get to this picture and just say that I produce 5 groups. And I know that some of the groups are really not very compatible with each other. So groups 3 and 5, for example, groups 3 and 5, for example, when either of them are present, they induce a 15% increase in the other one's chi-squared, essentially. Or sorry, not one present, one reweighted and upweighted. So that indicates that I should not include both groups 3 and groups 5. Happily, groups 2, 4, and 5, when taken together, cover all of the partial weights that I require access to. So they cover a good kinetical range. They give me access to all of the partial wave phase shifts and SSPs, which I need data for. Groups 1, 3, and 5 are actually relatively small groups that, when removed, get rid of most of the inconsistencies in the entire data set. And I want to emphasize that procedures like this don't tell me what's the real, important data. It just tells me what data that I have the best time fitting. One would hope that among all the experiments, the average is closer to the best, I don't know, real physical value, if I had ambiguities, if I had perfect data, stuff like that. But that's hard to say, probably not the case. The real solution is to build an experiment if someone has an idea for $1 million in their back pocket, and that would help.
I don't think they would want to
I don't know.
But what does it mean for the diagonal component to not be zero?
Oh, yeah, so those are within group compatibilities. So let me just say, so the clustering looks something like this, where I'm grouping them together based on how close they are and how directly compatible they are. That's not to say they're perfectly compatible, it's just saying that taken together, they share similar compatibility structures. So it's the diagonal parts is basically within group one, they're honestly not that compatible with each other. And that's sort of the best grouping that I can do for those experiments. Whereas groups 4 and 5 really like each other. Either group 5 basically just says it doesn't matter that the experiments that are in that group are in that group. And group 4 says that if you do both of these and weight them properly, then they agree very well. And I guess I'll just show really quickly one more time the grouping. So there's 3 experiments in group 1, and there's 1 experiment in group 3 that is. So those are the 2 that I'm discarding. So I get rid of 4 experiments, keep the rest, and then I'm doing very well for myself. Yeah.
If you talk to the folks from the party data group about, I mean, they must be doing this type of stuff.
Yeah, I mean, I don't know. I do, so my very last slide is comparison of like a sample pool. Here, I'm going to show you the bits and we'll get there. I have maybe 5 minutes. For the end of the day. So these are the bits with the reduced data set. They look lovely. All the data that I need is, all of the energy ranges in all of the data sets I have was roughly covered by some combination of experiments. Notably, I unfortunately did not completely disambiguate all of the gray area experiments. I was able to remove experiment gray A, and the other 4 are surprisingly fine with each other. Properly, one would do iterations of the same data selection to further refine, but it doesn't, like, no one really cares that much about the pounds, I would say, or the specifics. Like, really, you should have a physical reason for disambiguating rather than just it's one. So just 1 round is enough for me. The P1 and S0 phase shifts are well described.
So now you're sampling with the bands, right?
Those are not bands. That's every fit plotted simultaneously, actually. Because I like the pictures like that as opposed to bands.
Ah, okay.
Yeah. I think it looks cute as opposed to just 1 line with a band on it.
But why does the bulk right not account for the statistical errors? But yeah, I don't know.
Probably Roy, if I had to guess. I don't know.
What's the question?
The question is, why is the band on the top right in the S0 in elasticity, why is it so much smaller than statistical errors? And I would hazard a guess and say that Roy's been the size of the fluctuations there.
So there's not tiny, like some data with tiny errors, right?
Oh,
You mean below the elasticity? Or
No, I mean, I guess below it seems like it doesn't know all anything.
oh, you're saying the Martin azimuth.
It's true, there are also data points with very small errors, so it's mostly, like, the ones with the big errors are obviously more visible. So
This,
Yeah.
I mean, this is like,
Right.
your models are like two body models, right? So the only open threshold is the KK bar, so
Yes.
elasticity has to be 0 up to the KK bar threshold.
Yes. Oh, you're talking about the
Sorry,
low one.
elasticity has to be 1.
Yeah,
Are
yeah,
you
so
talking
it's constrained to be
1
1
or
below.
above 1?
It's,
no, I was talking about, yeah, below one, I understand.
Well, then, yeah, there's.
But it's true, there are a lot of data points with small errors as well.
Yeah.
It's just
Yeah, but
there.
this is only 1 data set in the large error bars.
maybe there's 2 in there, the greater B and the,
Purple.
So even if I did an old-fashioned chi-square, I probably would get a very narrow chi-square because of all the small errors, right?
yeah. I mean, I am doing a chi-square.
Yeah, but not an old-fashioned one.
Chi-square plus. Yeah, so the pits look cute, interesting. So there was the S2 and the B0. And now there's more wiggle room when you have less data, obviously. There's not really much to say, and the partial waves where I don't have that much data. So I'm going all the way up to the G2 wave. Notably, the D2 and G2 have known elasticity data, so it's assumed that those are pretty elastic. So that's something. It's a footnote in the paper that's older than me, so that's cool. And F1 is there too. Again, only 1 real set of data that has only 1 remaining set of data after the data selection. So yeah, so this shows that I can indeed interpolate the data at least and produce something that has unique output. And then probably the last, oh no, there's more. This is some plots used to describe to make sure the actual ensemble of networks is healthy. The one on the top left describes the approximate distribution, essential distribution of the weights present. So all of those values and all of those sigma matrices, linear stuff. They're clustered around zero. Most of them are zero, very close to zero, indicating that if I spend a lot more compute, I could probably compress the neural networks and get less, make it so that I have less parameters than data if I really try to. I will not do that because it makes the fitting a lot less efficient and takes longer to train if you have fewer parameters. If you would sacrifice flexibility for fewer parameters, and I already have too many parameters, so there's not really much gain there. The total loss looks fine, roughly healthy. Again, this is the sum of all the losses together. So it peaks around 4.5 or 5, which is not great, but still decent considering I still have incompatible data left over in my selected subset of data. Training time is, as I mentioned, quite fast. The longest runs took 230 seconds maybe. So it's not too bad. And then the bottom left two plots show histograms of the learned scattering length. So I'm saying, okay, neural network, what are the scattering lengths from the entire ensemble? The red vertical lines are the values as quoted by everybody who uses like normal analysis for these, who writes out an actual model. So we're in the same ballpark. We're not quite getting there. And there's really no way to determine why we're not exactly on their specific values. Between you and me, I would take my value over theirs because I didn't assume a model and they did, or at least my model was more flexible, so I reduced model dependence. But we're in the same ballpark. It's still.
What's the error
From theirs. Oh, on theirs. Oh, they're small. They're very their errors are very small, probably on the order of like on the order of 10% or less for there. So yeah, I'm not showing my error bars either. I'm not taking the actual propagation width here, but there's like a slight overlap there, or very close to overlap. And that's good enough for me. I'm not trying to reproduce those scattering lengths. And certainly not trying to put them in by hand. That would sort of defeat the purpose. Yeah, so I think I said all the things, all the bullet points, and then last comment, you can find, so for a simplified seed structure, for low energy type pi, you don't actually need to do the full analytic configuration that on the other sheet. You can just look for a 0 on the first sheet because it corresponds to that. The pull you're looking for corresponds to 0 on the first sheet, at least for the row in the sigma. So that's what I do very, very lazily, very quickly. Zero finding or pull finding is not the focus of the entire, whatever you call it, workflow. So I just selected like the top 50% of models, the ones that I just showed. Did a really quick pull extraction with a sequence of PEDs, so some sequence of rational functions that are guaranteed to converge if you run them long enough, and found these pulls. Again, they're not really. In principle, one should do a better job of selecting the models. I should just take the top half and then play with those with polls because I haven't done really any heuristics for saying this is how good the losses must be in order for it to be visible. But I'm in the ballpark, which is quite nice. So for the sigma, actually, I'm kind of on the money for the mass and the width, the sigma. The PG values are real. I did look at them this morning. They do claim that there's a 700 MeV range in which valid sigmas are allowed to be in, which is fine, I guess. I don't know.
That's not the one to compare. I don't think to compare is what
The Spanish group.
Oh, sure. Yeah, I mean,
It's the same, right?
yeah, it's roughly fine. Yeah, so I believe, I mean, we can pull it up in a moment if you like. And the row similarly, actually what's interesting is that the row's mass is underestimated from the neural network ensemble. And the width is somehow exactly on the width from the literature.
But the errors
are huge, and the errors are in large part due to the Wyatt equations, basically, or due to systematics coming from differences between the Wyatt equation representation of the amplitude and the neural network representation. So even 0.1 loss on average, or 0.05 for the ensemble was enough to produce sizable errors for this. And I will note that the systematic error due to that is not symmetric, it's biased, so these are the mass underestimated actually, so if I had written it better, it would have been more like 709 plus or minus like 16, like plus 50 minus something like that. Yeah, that's all I wanted to say. Down the mountains dry. Takeaways, you can describe pi scattering almost model agnostically, which is fantastic. That opens the door for a lot of analysis on newer, fancier resonances, hopefully with better quality data. Sort of, this was taking the worst case data and then showing that you can get the most obvious resonances, which is interesting. The error estimates from the Monte Carlo are important, great. You can do resonance full attraction with Roy, and please build me that experiment. Thank you.
I guess
There were a lot, right?
I'm sure Wyatt happy to answer.
Concerning your last
question.
point.
Yeah.
They want to travel to GSI, they have this own machine and they think about building pion.
They do.
Think about it.
They're thinking about it.
So it always helps. I mean, they have already a pion beam, but this I believe goes only to 600, 700.
Sort of formula, you know, their production of neurons.
Well, they principle, but they have to be a step, right? So they are.
I know it's a side project. Maybe
Beyond sensible measures, right? So
if you recombine things, you can use it.
I have so.
What is?
I will actually be able to do
Yeah,
that, right? That's what I-
Okay.
I wonder, pi scattering also includes to omega. Here it's very small. There's just 1% of the French ratio, right? So it's not.
So all they got-
Mostly three pi, so it does have became pi.
Yeah, I mean, I haven't really extended it to look above, outside of the low energy region, basically, sorry.
Well, the omega would have
Omega
very similar mass than the rho,
Oh,
and you, yeah.
Five.
So like,
The data got put up to tell what percent.
yeah, you would.
Very tiny.
yeah.
Yeah, I mean, it's the average.
So like in the E plus E minus experiments, they can also extract the delta one. And there you, because they have so much more precise data, they can see this small bump of the omega
Yeah, do you know how large?
hidden behind the huge bump of the rho.
You know how large this bump is on the data now?
It's very small compared to the rho.
Yeah,
So yeah, given the amount of data that's right there,
Yeah, I
then
just wonder,
I don't think you would be able to see
Yeah.
the omega.
to see the R ratio.
yeah, I will note that I'm not looking for it currently, and in the PET full extraction, you sort of guess how many poles you're looking for in the region here. I'm guessing one for the S0 and the S0. It's not very the most rigorous way of determining that.
Right.
Yes, yeah.
Do we really put this?
No, I was gonna ask another question. You don't have a collider of pi, but you have lattice data also.
Not precisely.
Like the
well,
same data that archives analyze with the raw equations from the lattice, you could analyze with this neural network.
So
Right?
now I want to ask him why he hasn't brought it up. You can read it.
Well, but lattice data would be in, for this kind of process, it would be in a much smaller energy range, right? Like this, like most of the energies here were like above 0.6 eV.
Okay.
But
You
then,
put that into the.
Yeah, one can certainly add those to the set. Yeah, I mean, look, I can fit even the noisy data, so I'm sure whatever data comes out of the lattice, I can deal with.
like, I guess my question is, what is the minimal set of phase shifts that you need for this to work? Like if you wanted to do this for 300 MeV pions.
Yeah, that's dependent on the Bohr equations, really, how many kernels you want to put in. So the kernels tell you like which ones are contributing, and the Bohr equations are one calculated for the S0, P1, and S2. So one could, in practice, reduce that set by using some kernels if there's no like G2 or F1 lattice data, which I doubt there will be.
There is very little, yeah.
Yeah. Yeah, so one can certainly do that. That just means that you would expect that the Roy equations become even more approximate because you're missing some partial ways. So yeah.
So you could do this for trigonometry.
Of course, you could do it for different ions if you want, yeah.
You'll have an openness data.
Yeah, so that's probably the limiting factor, though without trying it, I don't know.
Okay.
Wonder if you could apply to something which is one just in nuance to minus two discrepancies, experiments, which, pluses and minuses by pi. Experiments, some of them, one of them's really an outlier altogether.
Oh, okay, that is
Identify the
discrimination,
outliers.
yeah, I mean, everyone has their own favorite way of doing. A little more complicated than others maybe, but I tried to do an MPDS version, and then I found that I simply did not have the computing power to follow the combinatorial expansion of choices, because you look at one experiment, upweight it, and you find that it really should be used with some other sets, and then you do that for every experiment, and then so you put on like 20 different decision trees of reweighting. At every level, you see 2,000 more fits. It's just not possible. Folks say that it's bad.
Related to one of my two questions. Basically, go back to like one of the first slides where they had the data and the fit. So the first easier question would be. Oftentimes, very precise predictions come from the fact that your chi-squared sucks, like it's really steep, right? And that, for example, in this case, a huge discrepancy between purple and orange tables. And so that is oftentimes what limits the error quotient, because people can spoke plus or minus some signal, but if your chi-squared is super steep, error would fall. And so I'm wondering if they commented on, presumably the chi-squared is really fitting your size. It's not close to one.
Yeah.
Yeah.
I'm for data, it's 11.
And so that means the uncertainty estimate is probably also starting the parameters is taking out of the fit. Not you, but like when the.
Yeah.
So I don't know if
That's,
that's,
yeah.
I don't know if they're commenting on this.
No, their error bars are based off of a very so they do their chi-squared fit, and then from that chi-squared fit, then they refit, enforcing either Roy equations or other disparate relations using T2Y equations, just Roy equations recast, all disparate relations. And then their error bars are like a very tiny resampling around that.
But probably,
Yeah.
if we're not like inflating and certain data, they're uncertainty probably grossly that's too.
Yeah.
So my related question, which comes back to your discussion with reweighting of the experiment. So a different approach I've seen in a different field that people take this is two things. They say, one, let me take the quoted systematic uncertainty and actually treat that as essentially a normalization factor to multiply the data by, where that normalization factor is actually allowed to float. It's one of the parameters that gets to minimize the analysis. And the second thing people do is they say, let me assume there is some, you can think of it easily as extra stochastic uncertainty that somehow the experiment was missed that you need to add to all the data, or you could also think about it as an uncorrelated systematic uncertainty in each data point can fluctuate differently. And that's another parameter that gets added into the decision. We actually determine what this extra intrinsic missing uncertainty is not quoted is, and also some normalization factor. And that's a way where you can actually, the data can inform you through the fit process, how much extra uncertainty should you add in data sets, and also how much should you shift those data sets around. If you assume they're all true up to some systematic, it's kind of like, you can only do it in a Bayesian kind of.
Yeah.
That could be a way to redo this whole fit where it's sort of not exploding the numerical complexity.
Yeah, yeah, and I guess the main issue is that they are not all correct. One of the greater solutions is correct, and the other is a garbage.
Determined by. Yeah, what makes one correct and the rest garbage?
Because there's not enough information in the old experiment to say which one is correct, and so they just give all those issues. Physics does not, like, the scattering matrix is not multi-valued. They are incompatible with each other just from the single paper that produces them. But because I can't decide one over the other, I'll just say, this is it. So, yeah, I see how that would work. I think they would have to decide on one greater solution first, and then I would be able to try it. Yeah. Yeah, I mean, that's certainly possible.
So as far as you know, these authors did not do the PDG standard of inflate the chi-square or,
No, I don't believe.
until the chi-square for three and three goes to inflate the uncertainties.
Yeah, there's a large, so the body of literature surrounding the analysis of the facials, and there's a lot. Produces, like people have specific reasons for keeping or discarding certain experiments, and so these authors picked this set of experiment as the canonical best set. You know, a lot with what I'm doing, I think I'm definitely keeping all the N48 and the K stuff in this and then specifically all those rare solutions at hands at all, and I'm also adding N greater E and then something else that I affected.
The NA48 data is the most descriptive like that.
Yeah, it's also the highest quality set.
So if it's the highest quality, why is that quality picture about? That's what I was.
For them, I don't know. Yeah, so actually we have all the same data and I have the inclusion of layer E. Because so actually somehow I came to a similar conclusion with one specific procedure. With the inclusion of the greater E data, which is a few data points down to. I'll stop there, yes.
Let's thank Wyatt one last time.